Welcome to Marine Gurukul video series. You may use the details on the screen to connect with us for our online tutorial services.
Hi, this is Captain Sunil Bhaba from Marine Gurukul. Welcome to this video on turn planning of a ship. The turning of a ship onto a new course, commonly known as a course alteration, is a very routine and fundamental part of the ship's passage, but a very critical maneuver. It is very easy to monitor the progress of a ship when it is moving along a straight line path. But while turning, the ship actually follows a curved path, making it challenging for the navigator to monitor the ship's progress. It becomes all the more important to get this part of navigation right, especially when the ship is proceeding in restricted waters close to navigational dangers. As in such a situation, even a slight doubt or any uncertainty on the part of the navigator could lead to a major disaster. The straight line courses which are present on the chart may be running in safe waters, but the curved path which the ship actually follows while turning may take the ship onto danger. In this video, we are going to explore the basics of turn planning. We will see what are the factors which decide the curved path which the ship follows while turning. We will also understand the relationship which is used for turn planning, that is rate of turn is equal to V upon R, or rate of turn is equal to V by R. And we will also see its practical application or its use through a simple numerical based on actual turning scenario of a ship. This knowledge and understanding forms the basis for successful planning, monitoring, and execution of the ship's turn. So with this understanding, let's jump into this interesting aspect of the ship's passage planning. Let us now try to understand the concept, the fundamental behind turn planning. Unlike road vehicles, a ship does not turn sharply, reason being lesser friction offered by the water and also the influence of momentum. Whenever the vessel alters its course, the vessel actually moves along a curved track which can be treated as an arc of a circle. Let's try to understand this using a diagram. Let us assume that this is the initial course of the ship. You can follow the laser pointer. At this particular point, we have a course alteration. This is point delta. So at this particular point, the vessel has to alter its course, and this is our final course. Now, even though the courses are shown as straight line tracks and the course alteration is shown at point delta, the vessel will not move along these straight line track while it is altering its course. Vessel will be moving along the arc of a circle, basically the turning circle of the ship. Let us now show the curved path on which the ship actually moves. You can see this maroon color arc. Now this is the actual track on which the ship will be moving when it is altering its course. The vessel will be initially moving on the initial course up to this particular point, that is this tangent point of the arc, and after this point the vessel starts to travel on the curved path and it follows the curved path up to this point here, which is again a tangent. The final course is tangential to the turning arc here, and from this point onwards the vessel again starts to move on a straight line track, which is the final course of the ship. Now in case of small ships, these arcs are also small. In case of a small vessel, the arc could be much smaller with a much smaller radius, as the turning circle of small ships are much smaller. But for large vessels, these arcs assume greater radii. Now for a large ship having a larger turning radius or a larger turning circle, the track on which the ship will be moving will be this one. So for larger ships, these arcs on which the ship moves when it is altering its course assume greater radii, and they need to be treated differently. We can also easily find the center of this turning circle or center of this arc. In the coming slides, we will be seeing how do we identify the center of the turn, how do we mark this curved path on our chart. So let us for the time being show the center of the turn. You can see this is the initial point A. The vessel moves on the initial course up to point A. From point A, it starts to move on the curved path. It moves on the curved path up to point B. And from point B, Bravo point, it starts to again move on a straight line track, which is the final course. This is the center of the turn or the center of the turning circle represented by C, and Charlie to Alpha or Charlie to Bravo represents the radius of this turning circle. For a small ship, the radius will be smaller and you will have a small arc like this one. But for a bigger ship whose turning radius is bigger, you will have a greater radii arc like the Alpha Bravo AB arc shown on the screen. Now for small ships, if you look carefully, the arc is not much far away from the straight line tracks. But as the size of the ship becomes bigger and bigger, the turning radius becomes bigger and bigger, these arcs are at a substantial distance from the straight line track. Now it is possible that the straight line track of the ship may be following or going through a safe path, a safe passage, but this curved path may be passing over a danger. So it becomes very, very important for us that whenever we are planning our passage, we mark these curved paths on our chart or they are marked on our EGDIS, and we check the safety of the curved path, because this is the actual path where the ship will be moving. The vessel will not be moving on straight line track from Alpha to Delta and Delta to Bravo. It will be moving along this arc Alpha to Bravo. So it becomes very, very important to check the safety of the passage along this arc and ensure that the curved path is not passing over any shallow patches or navigational dangers. So this is the importance of planning a turn in a passage plan. We need to identify this curved path on our chart or on the EGDIS. We need to check the accuracy. We need to check the safety of this curved path, that it is running through safe waters, not running over shallow patches or navigational dangers. Now the first concept which we need to understand for the purpose of turn planning is the derivation of the rate of turn formula. So let us try to understand how do we derive the rate of turn formula. We have seen this particular ship moving on the initial course up to point A, then moving on the curved path from Alpha to Bravo, and then moving on its final course. Let us assume that the radius of this turn, which has been planned for this particular ship, is R. So let us represent Alpha to Charlie, which is the radius, as R. The Charlie to Bravo radius will also be R. Let us also assume that the angle by which the vessel is turning is theta degrees. So this angle represented by this yellow shaded portion by which the vessel is turning is theta angle. The vessel is moving on the arc from Alpha to Bravo. Now, by the definition of an angle in radian is basically the ratio of arc of a circle to the radius of a circle. Using this definition on our course alteration angle theta, the angle theta in radians should be equal to the arc, which is alpha bravo, divided by the radius of the turn. Now this distance alpha to bravo, or the arc alpha to bravo, can be easily obtained by using the formula distance is equal to speed into time. The speed of the ship, let us assume the speed is v knots, and the time taken for the alteration is t hours. The time has been taken in hours here because the speed is given in the units of nautical miles per hour. So time has to be used in hours. Divided by the radius of the turn, the radius will be in nautical miles. Now in this formula, we would like to see the angle in the format or in the units of degrees. Degrees is the unit which we normally use on a ship. We do not use the radians. So we would like to see the angle here in degrees, and also the alteration of a ship is done in a matter of minutes, not in hours. So we would like to have the time here in minutes instead of hours. So let us convert these radians to degrees and hours to minutes. For that, we should be aware of that 1 radian is equal to 57.3 degrees. So in this formula, instead of writing the angle in radians, I want to input my angle in degrees, and this angle input in degrees divided by 57.3 gives me the same value as the angle in radians. Going to the right hand side, we have the speed v in knots multiplied by time t in minutes. So this time has been converted into minutes now instead of hours, and this t minutes divided by 60 gives us the same value as the time in hours. So in the denominator we have the radius as usual in nautical miles. So you can now see radians have been converted to degrees and the time has been converted to minutes. Now what we do is these t minutes term is taken to the left hand side. It comes in the denominator here. So theta degrees upon t minutes is equal to v knots multiplied by 57.3. This 57.3, which was at the denominator on the left hand side, is now taken to the numerator of the right hand side. So v knots multiplied by 57.3 divided by r in nautical miles multiplied by 60. Now the term which you see on the left hand side, that is theta degrees divided by t minutes. Theta is the angle by which the ship is turning, and t is the time which the ship takes to complete the turn or the alteration. This is what is known as the rate of turn of the ship. So rate of turn is equal to degrees by minutes. These are the units of rate of turn. The ship is turning at a rate of so many degrees per minute. This will be equal to v in knots divided by the radius in miles. V is multiplied by 57.3. Radius at the denominator is multiplied by 60. Now if you look carefully, the numerical terms which we have on the right hand side, 57.3 in the numerator and 60 in the denominator, are close to each other. So these terms being close, without any appreciable loss of accuracy, these can be cancelled out and the formula gets simplified to the rate of turn equal to v upon r. So this is the rate of turn of the ship in degrees per minute. This is the rate at which the ship is turning, and it is equal to the speed of the ship in knots divided by the radius of the turn in nautical miles. So this is the formula for rate of turn of the ship. Now this formula gives us a very good insight into the turning of a ship. In this formula, the speed of the ship on the right hand side and the radius, both of them are in the navigator's control and they can be altered as required. The rate of turn which we see on the left hand side, which can be achieved on a particular ship, is not entirely under the navigator's control. The maximum rate of turn which can be achieved on a ship is limited or depends upon the size of the ship. It depends upon the shape of the hull, the block coefficient, what is the size of the rudder, the maximum rudder angle which is available to the navigator at the time of alteration. For example, on a particular ship, the rudder angle which may be available to the navigator could be 10 degrees or 15 degrees or 20 degrees in open sea. So the maximum amount of rate of turn which we can achieve is limited in a particular ship. So the speed and the radius should be selected in such a way that the resulting rate of turn is achievable in the present conditions. So whenever a turn is planned, it should be kept in mind that the speed and radius has to be adjusted in such a way that the resulting rate of turn is achievable for that particular ship. Now whenever we are in open sea, usually the speed is not touched, not varied, and the radius can be adjusted as per our requirement. So to achieve the required rate of turn, we can modify the radius of the turn as required whenever the vessel is in open sea. However, when we are in restricted waters, the radius may not be under our control. It may not be possible to adjust the radius as per our requirement. So in those situations where the radius cannot be altered because of restricted waters, navigational dangers, then the speed has to be maintained in such a way that we have an achievable rate of turn. Now many times when we are making a passage plan on EGDIS, the EGDIS also gives us an alarm that a particular turn is not executable, indicating that the rate of turn which is required as per the speed and radius fed in by the navigator is more than what can be achieved on that particular ship in the present conditions. So in such a scenario, when you get an alarm on a EGDIS passage plan that the turn is not executable, you will need to alter either the speed of the ship or the radius of the ship in such a way that the ROT comes under the achievable value for that particular ship. So as discussed, in open sea, the radius can be altered. There is no need to touch the speed. And if we are in restricted waters and it is not possible to modify the radius, in that case, the only option available to the navigator is to reduce the speed of the ship to make the turn executable. So you see, a basic understanding of the ROT formula gives us a insight into the turn planning of the ship. And if you understand these parameters, it becomes very easy to modify and make the turn executable. Let us now see the practical relevance of this formula. How does it help us in actual situations, actual scenarios on board? Let us understand this using an example. We have a vessel which is moving on an initial course of 010 degrees true, and the final course is 080 degrees true. She is doing 15 knots of speed and she intends to turn about an island or islet, keeping a distance of 1.5 miles. So basically 1.5 miles is the radius of our turn. We need to find out what will be the rate of turn and how long will the ship take to complete the turn. So let us try to solve this using the concept of rate of turn what we have understand till now. So let us first make a diagram of the situation of the data which is given to us. You can see the diagram on the screen now. Vessel is moving on a initial course of 010 degrees and the final course is planned to be 080 degrees, and the vessel has to make the turn about an island. Let us assume we have the island here at this particular location, which will be the center of our turn, and the radius of the turn is assumed to be 1.5 miles. So you can see the radius of the turn Charlie to Alpha denoted as 1.5 miles. Then Charlie to Bravo denoted as 1.5 miles. So let us now apply the formula and see what results do we get from there. We know from the rate of turn formula, rate of turn is equal to V upon R. The speed is given to us as 15 knots and the radius of the turn is given to us as 1.5 miles. So this tells us that to execute this turn, the vessel needs to maintain a rate of turn of 10 degrees per minute. So the first thing which can be done is we can evaluate whether the vessel is able to do or achieve this much of rate of turn or not. This may be very easy to achieve on a small ship or a medium-sized vessel, but it may be difficult to achieve if you are on a very large ship. So this is the first utility of the formula. We get a value of the rate of turn and we can evaluate whether this turn will be executable or not. Now we know that the vessel's rate of turn needs to be 10 degrees per minute to execute this turn. The amount of alteration which we have is 70 degrees. Initial course is 010 and the final course is 080 degrees. So vessel has to alter by 70 degrees. Now the vessel is altering 70 degrees at a rate of 10 degrees per minute. So the total time which the vessel is going to take is 70 degrees divided by the rate which is 10 degrees per minute, and it comes to 7 minutes. So from point alpha, when it starts to move on the curved path, up to point Bravo, when it reaches on its final course, the vessel is going to take a total of 7 minutes to complete the turn. So we know what is the rate of turn required. We also know what is the time which the ship is going to complete the turn, giving us an understanding of the turn, and we can now easily plan this turn if these parameters are within our control or they are achievable. I hope this video added value to your understanding of the topic and certainly will be of use in case you face any issues while turn planning on board. Please do comment. Please do like and share our content. This motivates us to generate more content similar to this one. Also, this helps these kind of videos reach out to more people. In case you need any further support, please write to us on marinegurukul@gmail.com. Thank you very much for watching this video. I wish you all the best.